Hi everyone, welcome back. Today in this session we are going to solve the problem 3 using ANSYS. Now this is a statement of the problem. A compound bar is loaded as shown in the figure. It's a step bar fixed at one end having two different materials, that is steel and copper. In this also we need to calculate the displacement, strain, stress and the reaction. And once again we need to consider 1D bar element and the Young's modulus for two different material he has mentioned. That is Young's modulus for steel is 2 into 10 to the power of 5 Newton per mm square, and Young's modulus for copper is 1 into 10 to the power of 5 Newton per mm square. Before going to the answers, let us go through the values what we have calculated using FEM approach. So the displacement at fixed end is 0, that is U1, and the displacement at the junction between the two material, it is U2, that value is 0.141 mm, and similarly the displacement at free end is 0.538 mm, that is the value. Then strain, if you check in the steel, it is 1.76 into 10 to the power of minus 4, and strain in the copper, it is 7.94 into 10 to the power of minus 4. Similarly, the stress in the steel portion, it is 35.25, and the stress in the copper portion is 79.4 Newton per mm square. And finally, the reaction at the fixed end is 99,670 Newton, which is nearly equal to 100,000 Newton, nothing but 100 kilonewton. So these are the values through solved through FEM. Now let us check the values using the ANSYS software. Now I'll open the software. So this is my ANSYS software. Let us start with the preference. In the preference, I need to select the structural. Okay, it's a structural analysis. Now in the preprocessor, I need to select the element type for the analysis. So add the element. Now once again, it's a one-dimensional analysis. Therefore, I need to select the link element. So you select the link element, then you say OK. Then close this menu. Now after selecting the element, now I need to select the real constant, where we need to define the areas for those two step portions what we have considered. So I'll go to the real constant, add the real constant for that selected link element. Okay. Now the cross sectional area of the first portion, which is a steel portion, that area is I have given 60 mm diameter. When I convert that in terms of area, it is pi by 4 into d square. When I put all the values and put the calculator, it will be 2827.43 is the value. Then I'll say apply here, because I need to enter one more area. So I'll say apply. Now I'll change the real set constant number to 2. Then I'll enter the area for the second, that is copper portion, where I given the diameter as 40. Once again, pi by 4 into 40 square, the value will be 1256.63 is the value. So these are the two areas I entered. Now I'll say OK. Then I'll close this menu. Then after that, I need to enter the material property for both the material. So I'll go to the material properties, material models, then structural, linear, elastic, isotropic. Then the first material is I am going to consider it as a steel, and that value is 2 e raised to 5, and as it is a one dimensional analysis, I'll put the Poisson's ratio 0, and I'll say OK. So this is the first material value I entered. Similarly, I need to enter the another material. So for that, I'll go to the material here at the top. Then I'll say new model. Now it is a material number 2. It is going to define. So under material number 2, the isotropic value I need to enter nothing but it's a metal property which is for the copper portion, and that value is 1 e raised to 5 is the value, and once again it's a one dimensional. Therefore, I'll take Poisson's ratio 0. Then you say OK. These are the two material values I entered. Now I can exit this. So go to the material and say exit. Now after completing this metal property, I'll come to the modeling. Now in the modeling, I need to create the nodes. So for that, I'll go to the create nodes in active coordinate system. So I'll create the first node which is at the origin. So I'll put x, y, z values as 0, and I'll say apply. So second, I need to create from the origin at a distance of 800. Then I'll say apply. Similarly, third, I need to create at a distance of 1300. Nothing but the value of copper portion is of 500 mm, but it is calculating from the origin. Therefore, it is 800 plus 500. The total value will be 1300. That is the value I need to enter. Then I'll say OK, because this is the last node. So I'll say OK. So these are the three nodes which are created on the screen. Now I need to create the element between these three nodes. Let us change the color here so that it will be better for visibility. Okay, so these are the three nodes. So now I need to create the element between these nodes. For that I'll go to the elements. uh, in the previous sessions you have directly created the element between node number 1 and 2 and between 2 and 3, but in this problem you please take care that I have a first portion which is of steel and second is of copper, where the values are metal properties are different. Therefore we need to call out that particular metal property while creating that particular element. So when I come to the first portion, it is the steel portion. The Young's modulus for steel portion is 2 into 10 to the power of 5, and area is also different value. Therefore, you please remember where you have created those values, and in that particular attributes you have to call out. So when you go to the element attribute here, I have the material number 1 here. So first material number I have created it as a steel, and real constant also I have created for the steel. Therefore now it is okay to create the steel portion. So when material number is 1, when real constant set number is 1, so you can create the element for the steel. So I'll go to the auto number here, then through nodes, then you select the node number 1 and 2 and you say okay. So this is the element I have created for the steel. But when I am creating element for the copper, now area is also different, and the Young's modulus value is also different. Now I need to call out that those values. For that you please use this element attributes. Go to the element attributes. Now material number you change it to 2, and real set constant also you can change it to 2. There we have defined the values of copper and copper for area of the copper as well as Young's modulus of the copper. Those are the two values I have selected. Then you say okay. Then once again come to the auto numbered through nodes. Now you select the node number 2 and 3 and you say okay. So this is what the creation of the element when it is made up of two different material. Now when I go to the isometric, when I say plot and when I say multiplot, so these are the two elements. Now I can check this in the form of three dimensional. For that you go to the plot control at the top here, then go to the style, then you click on the size and shape, then here display of the element you switch it on and you say okay. Now this is what my three-dimensional view of that whatever the step bar I have created, where the first portion is having a larger area, whereas the second portion which is having a smaller area compared to the first portion. So this I can switch off for the next process. Just I have shown how it look like in the form of 3D. Okay, this is my the elements I have created. Now I'll go to the creation of the loads. For that I'll go to the load section, define loads, apply structural displacement. Now I need to apply the displacement on node, so I'll select on node, select this node number 1 where it is completely constant and you say okay. Now I need to fix all DOF, so I'll select all DOF and I'll say okay. Now this is what the node which is completely constrained. Now I need to apply the force at node number 3 and that value of the force is 100 kilonewton. So for that I'll go to the force on node, select node number 3 and you say okay. Now it is asking in which direction I need to apply the force. Now force will be applied in the x direction, therefore I'll select Fx and it will ask you to enter the value. The value of that force is 100 kilonewton, therefore I'll enter the value in terms of Newton. It is 100 e raised to 3 is the value. So after entering this value you say okay. So this is the force of 100 kilonewton applied at the free end. Once the force is applied, now my problem is ready to solve. Now I'll minimize all the sections under preprocessor. I'll go to the solution. Under solution you select solve and you say current ls, solve the current ls and you say okay. Now once the calculation is done at the backend, it will say solution is done. Then you close this. Now I need to call out the result. For that you go to the general post processor. Under general post processor you go to the least result. In that you select the nodal solution. Now as force is applied in x direction, once again you will get the displacement in x direction. So you select DOF solution, x component displacement and you say okay. Now these are the displacement which are there at different nodes. So node number 1 is completely constrained, therefore the value of displacement at node number 1 is 0. And the value of displacement at node number 2 is 0.14147 is the value in terms of mm, because I entered the value in terms of Newton and mm. Similarly, the displacement at node number 3 is 0.53936 is the value. These are the three displacements. Now I need to check the values of strain and stress. For that I need to create the element table. I'll go to the element table, define table, add, then pull this down, select by sequence number, then you select this ls, give the number 1, first result, apply. Similarly, pull this down, go to the by sequence number, LEPL, you give the number 2, second result, okay. Now once these two results are called out, close this menu, once again come back to the list results, then you go to the element table data, under that you select both ls1 and lepl2 and you say okay. Now once again I have two elements here, therefore it has shown the two number 1 and 2 and corresponding stress and strain it has shown. So for element number 1 the stress is 35.36 Newton per mm square and the strain in the first element, that is in the steel portion, is 0.176 into 10 to the power of minus 3. Similarly, for the second element, that is for the copper portion, the stress is 79.57 Newton per mm square and the strain is 0.7957 into 10 to the power of minus 3. So minus 3. So these are the values of stress and strain. Now once the stress and strain are calculated, now I need to check the reaction. For that, I'll go to the reaction solution, which is there in the list result. Under list result, reaction solution, and applied force is in x direction. Therefore, reaction I'll get it in x direction. So you select structural force Fx and you say OK. So this is a reaction and it will show the location of that reaction, which is there at node number 1 because that is the node I have constrained. Therefore that value is minus 0.1000 e to the power of plus 6, nothing but it is 100 kilonewton only. So this is what the reaction, and this is what the solution we have done through the ANSYS. Now I'll go back to my presentation. There I'll show how it can be compared with the FEM. Okay, this is the table where I am comparing both FEM approach as well as ANSYS. So my U1 is 0, both both cases. My U2 is 0.414 in case of FEM, here also it is same. U3 is 0.538, here also it is 0.39, nearly equal. And the strain in the steel portion is 1.76 into 10 to the power of minus 4. Here it is 0.176 into 10 to the power of minus 3, nothing but after shifting this digit to 1 point forward, it is 1.76 into 10 to the power of minus 4 itself. So then it is 7.94 into 10 to the power of minus 4 for copper. Here also it is 7.95 into 10 to the power of minus 4. Then the stress in the steel is 35.25 Newton per mm square and here also it is 35.36. Then the stress in the copper is 79.4, here it is 79.57. Then coming back to the reaction, the FEM approach given a value as 99.67 kilonewton and it is 0.1000 e to the power of 6, nothing but it is 100 kilonewton. So that is what my applied force. So this is how the comparison done and obtained the same values through the ANSYS. Thank you for watching.